In section 5, we are concerned with drawing and describing the cyclic forms of sugars. There's a lot of structural drawing, there's a lot of new terms and definitions, and stereochemistry. So we'll try to take it slow, be very thorough in our explanations, and this is by far going to be the longest section in your textbook. I count 10, close to 9 pages here in our textbook. So let's get moving through this section here. The first thing we want to do is review acetals. So remember that if you have a aldehyde, this can react with an alcohol, usually under acid condition, to give you a hemiacetal. The other components here that are not drawn are water. I'm sorry, not water. What I wanted to show here was the hydrogen that's missing. I'll just draw it here, just in case you're wondering, well, where did that H go on the aldehyde, okay? So this is kind of like an addition reaction. The methanol adds across the carbon-oxygen pi bond. The OCH3 adds to the carbonyl carbon, and the hydrogen adds to the oxygen atom of the carbonyl. Now, normally this reaction lies greatly to the left, okay? Because of all the bond strengths and things like that involved. There's no driving force for this reaction, and the aldehyde is more stable in the free form, okay? Now, cyclic acetals form when the alcohol is present within the aldehyde, okay? So if we have something like this, it's usually best if we draw it kind of wrapped around like a snake ready to bite its own tail. And here it kind of makes more sense now why this oxygen atom of the alcohol would attack itself and attach to the carbonyl, and why this hydrogen would attach to the oxygen, okay? So again, think about this as an addition reaction. The oxygen connects to the carbonyl carbon, and the hydrogen goes to where the oxygen is. So when this happens, so these two are equivalent. That's the mathematical symbol for equivalency. If we were to add H plus to this, the cyclic acetal is actually more stable on grounds of entropy, okay? So if we draw the product here, we're going to see that we're going to form a cyclic acetal. I'm sorry, hemiacetal. So this is a cyclic hemiacetal. Now, I mentioned entropy. If I might highlight this reaction in yellow up above, we have 2 particles forming 1 particle, and that's not very entropically favored, okay? However, this reaction right here, you're going from 1 particle to 1 particle, so there's no penalty in terms of the entropic cost or the entropy of this transformation. So that's why the cyclic hemiacetal is more favored, and this is why sugars always exist in the hemiacetal form, or the cyclic hemiacetal form, rather than the open chain that we draw when we draw the Fisher projections, okay? Let's just jump in. You can read more about the example here, but let's just do some problems here. Problem 24.9. So problem 9, we're just interested in reviewing cyclic hemiacetals. We're not talking about sugars yet, okay? So the textbook example recommends numbering the carbons. I would as well. And so I'm going to do 1, 2, 3, 4, and then my oxygen is the 5th atom, okay? So I'm going to draw a nice 5-membered ring where the oxygen is the 5th atom in this ring, okay? And then I'm going to use this as a template, and I'm going to number things. So 1, 2, 3, 4, and I'll just number the oxygen atom 5, okay? Attached to carbon 4, we have 2 methyl groups. Okay, so don't forget to add your carbon groups, your phenyl ring, your whatever might be present, okay? And then carbon 1, this is where you're going to add your OH group, okay? So that right there is the acetal or the hemiacetal carbon or the carbonyl carbon that's now masked, okay? For B, we want to do a similar thing. Let's number the longest chain here. Okay, and I'm going to number the oxygen atom number 6. So this is going to be a 6-membered ring. Draw a 6-membered ring with your oxygen in there, and then just number things. It's okay if you number counterclockwise if you want. It's not going to matter. Okay, so let's go ahead and add our things. The carbonyl carbon is carbon 1, so this is where we're going to add our OH group to our drawing to indicate the hemiacetal. Carbon 2, 3, 4, we don't need to do anything. Carbon 5, this is where we need to add the 2 methyl groups, so there's a methyl, okay? Carbon 6, let's go ahead and number our carbon atoms and the oxygen, okay? So here you want to draw a 7-membered ring. It's quite challenging. I certainly can't draw it fast, and that's kind of as best I can do, okay? Go ahead and number around the ring. I'm gonna number the oxygen as the 7th member of this heptagon, and then we wanna go ahead and add things. So carbon 1 is gonna be the hydroxyl group. Carbon 3 is gonna have 2 methyl groups. Okay, it's easy when you have numbering. 1, 2, 3, 4. The oxygen is the 5th membered, so we're going to draw a 5-membered ring. Go ahead and number this. Okay. Carbon 1, we're going to have the hydroxyl group. Okay. And carbon 1 also has a methyl group here. Okay, there's a CH3. That line means a CH3, so I'm going to add that CH3 here. Carbon 4 has 2 methyl groups. Okay, so that's how I would do this problem. Now I want to discuss the pyranose forms of monosaccharides. Okay, so here's a nice diagram that shows the pyranose forms of monosaccharides. And again, take note of the equilibrium. That top arrow pointing to the right is longer, which means that the favored form of the sugar is for it to be in this closed hemiacetal, okay? And so what you're doing is you're taking this hydroxyl group, the one that defines whether a sugar is D or L. They're all D, by the way, right? And so that's going to wrap around and connect to the aldehyde carbon at carbon 1, okay? So if you can number the atoms of the ring, it's going to be 1, 2, 3, 4, 5, and then the oxygen, I would actually number that atom 6, right? So that's why you have a 6-membered ring, 1, 2, 3, 4, 5, 6 as numbered here, okay? It's kind of hard to see it here in the Fisher projection, okay? The Fisher projection or Fisher diagram. But in the kind of cyclic form here, it might be easier to see, maybe not. And then on the right, we have a flat 6-membered ring. We definitely know that cyclohexane is puckered. It has this very beautiful chair cyclohexane. There's these 2 chair forms that you can flip and do all that kind of stuff. But here on the right, this is called a Haworth projection or a Haworth drawing. Okay, so we're going to use this a lot. Okay, so all of the atoms stay the same. And what you're basically doing is you're changing the carbon 1 here, which is an aldehyde originally, into just the OH group there. Okay, so that's what we do here. So this is a pyranose ring. A pyranose ring is a 6-membered ring with an oxygen in it. Okay. So that's the first definition, all right? Now, it turns out that this carbon 1 is the anomeric carbon. So let me show you what we mean by that, okay? So if we take our glucose molecule and we cyclize, we can generate this isomer. Or we can generate this isomer. Okay? Now, the reason why is because in an aldehyde, right? Remember, the aldehyde looks like this. Carbon 1 is here. The aldehyde is not a stereocenter because the carbon only has 3 groups attached to it. It's trigonal planar. But when you form a cyclic hemiacetal, carbon 1 is a newly created stereogenic center. Okay, this one here is called the beta isomer or the beta anomer. Okay, and this molecule on the right is the alpha isomer or the alpha anomer. Okay, the alpha anomer has the OH group pointing down. The beta anomer has the OH pointing up. These two molecules are called anomers. Anomers are molecules that are stereoisomers at the anomeric carbon, carbon 1, which is the result of this cyclization process, okay? So carbon 1 is the anomeric carbon. And that's also the anomeric carbon. Now, these two molecules are in equilibrium with each other. I'm not going to describe right now which one is more stable, but the process by which you go from the left anomer to the right anomer is called mutarotation. The only way for that to happen is if your hemiacetal reacts with acid and opens up, forms the aldehyde, and then the alcohol, right, at the carbon 5 is going to attack from maybe the bottom face instead of the top face, okay? And that's going to give you the different anomer. So that process by which these two equilibrate is called mutarotation, okay? So I've discussed the pyranose ring, I've discussed the anomeric carbon, I've discussed anomers, I've discussed the alpha anomer, and I've discussed the beta anomer. All of these terms are bold in your textbook, so when you read them, pay very close attention to them. Okay? So, as usual, the cyclic acetal is the major structure that you have. Okay? So let me show you a new figure that shows this mutarotation process. Okay, so this figure is very nice. It shows you how mutarotation can occur, okay? So let's take, for example, this molecule here on the bottom left. It's called alpha D-glucopyranose, okay? Gluco is coming from glucose. That's this sugar, well, it's showing the cyclic structure there. But this molecule up on top is called glucose, okay? Top center is glucose. So that's glucose, it's a sugar. It's a D sugar because remember again, this hydroxyl group is showing on the bottom, on the right for the bottom hydroxyl group, okay? So it's derived from D-glucose. Now we call it D-glucopyranose because it's a cyclic hemiacetal with a 6-membered ring there, okay? And it's called alpha, remember, because this OH group is pointing down. Now if this molecule were to react with H+, okay, that would convert that molecule into a good leaving group, and this can break apart to give you, sorry, I protonated the wrong way. If we, these lone pairs here could reform the carbonyl, and this could, you know, break off if that were protonated. And that would give you the aldehyde shown right here, top center. Now, when that hydroxyl group decides to attack the aldehyde, it can do it from the top face or the bottom face. Remember, an aldehyde is trigonal planar. So the OH group could attack from the top face of the plane or the bottom face of the plane. And let me just highlight that in green here on the slide, okay? So here's your aldehyde and it's planar. When the OH attacks the aldehyde from the bottom face, you're going to get this, well, I won't say, you know, we don't really need to worry about that. But if the OH from carbon 5 here attacks the top side of the aldehyde or the bottom side of the aldehyde, that's what gives you these two molecules here, the alpha D glucopyranose and the beta D glucopyranose. So that's a great diagram which kind of shows how they are, okay? Now, one of the skills that we need to be able to have is to actually draw the Haworth projection, either the alpha or the beta isomer, given our Fisher projection of our sugar. So let's take a look at the pattern here so we can recognize how things are working, okay? So at carbon 5, that's your OH group, okay? So that's going to be the oxygen that's part of your cyclic acetal. Carbon 1, that's going to be where your hydroxyl group is on the hemiacetal, either pointing down or up, okay? The other OHs, if we can look very carefully to it, is that you'll notice the pattern. If the hydroxyl group is shown on the right side of the Fisher projection, it's going to be pointing down in the Haworth projection, okay? So right on the Fisher is down on the Haworth projection. And if you look at the carbon 3 here, this hydroxyl group is pointing to the left. And if we could look where it ends up here, it's going to be on the top, okay? So left is top, right is down, okay? So let's do the example in the book here, and let's draw what we have, okay? So first, I like to number my ring carbons a little bit differently. I start with carbon 1 here on the aldehyde, 2, 3, 4, 5, and then I take a turn to the immediately possible 6-membered oxygen, okay? So you always start by drawing your 6-membered ring with the oxygen in kind of the top right corner. So you're gonna start with this as your Haworth template, okay? So here's your template, all right? And so your OH, you have the choice of what you need to do. The example says to draw the structure of the alpha D galactopyranose. Okay. Alpha isomer, you need to memorize where the OH is. The OH is pointing down. So I'm going to position the H here and the OH down, okay? That's carbon 1. That's carbon 1 of your aldehyde. So we move over to carbon 2. Here's the OH. Remember, if the OH is pointing to the right, we point it down in the Haworth projection. Here's carbon 3. The OH is pointing left, so therefore we point it up in the Haworth projection. Here's carbon 4. The OH is pointing left, so we point it up in the Haworth projection, okay? And then we have this CH2OH group, okay? And that's going to be pointing up like so. Okay? Problem 12, draw a Haworth projection for each of the following compounds. Beta D galactopyranose, okay, we just basically did that, but we did the alpha isomer, so I don't want to do that one. Let's do this new sugar, alpha D manopyranose, okay? And let's do this new one, alpha D allopyranose, okay? So the first thing you need to do is look up mannose and draw the Fisher projection for this. Now, you don't know if this is a ketose or an aldose, and you don't know how many carbons it is. So you just kind of have to flip through the book and find it, okay? When I give my exam to my students, I usually just give them a chart of all the sugars, okay? Step 2, number your carbons and the oxygen to form a nice 6-membered ring. Remember that if you have pyranose, that's a 6-membered ring. We'll talk about furanose later, which is a 5-membered ring. So for now, we're doing 6-membered rings because pyranose means 6, all right? That's what you need to remember. So carbon 1, 2, 3, 4, 5. What oxygen is going to be 6? It's going to be this guy right here, okay? Step 3, you want to draw your template as follows. And you want to position the hydroxyl group on the correct location. We want to draw the alpha isomer, which means it's going to be pointing down. Next, you want to draw tick marks for the other carbons and position them appropriately, okay? If the OH is left in the structure, you point it up. If it's pointing right, you point it down, okay? So carbon 2, OH is left, we point that up. Carbon 3, OH is left, we point it up. Carbon 4, OH is down. OH is right, so we point it down. And our last carbon is the CH2OH. We put that up here, okay? And the other hydrogen is going to be here, okay? That's how you do that problem. On the next page, let's do alpha D allopyranose. Pyranose means 6-membered ring. Let's try to find, does allose get its name because all the OHs are pointing to the right? I don't know, maybe. So let's count the carbons. And our 6th oxygen is off to the side, okay? Build your template. Go ahead and put the hatch marks on each of the carbons. And decide what you're going to do at carbon number 1, okay? Carbon number 1 needs to be in the alpha configuration. So alpha means up. If your OH is pointing to the right, we create the OH pointing up on the, if the OH is pointing right, we make the OH pointing down on the Haworth projection. So we're going to have all of these guys pointing down, 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 okay? Next, we have CH2OH on the remaining, and we fill in the H's everywhere, okay? So that right there is alpha D pyranose, okay? I urge you to do the rest of these on your own and Google, find out if the structure you've drawn is the correct Haworth projection, okay? It's easy to check these. Next, we want to talk about the 3-dimensional structure of the pyranose rings. So when you have a Haworth projection, we realize that this is not a flat-membered ring. It's a chair cyclohexane ring, okay? So we normally take this carbon and bend it down, and take this carbon and bend it up, and that creates your chair ring system, okay? All right, so up in this diagram means up in this diagram. Remember in, chapter 4 of Organic Chemistry 1, you probably talked about chair cyclohexanes, and if you took my class, we talked about uppers and downers. Up carbons might be axial or equatorial, but they're always up. Downers or down carbons have substituents pointing down. They could be, equatorial axial as well. So you need to position all of these as so. This OH is up, okay? This OH is down. And then you've got a couple of groups here. What's next? I lost my orientation. So there's carbon 1, 2. We're on carbon 3. Carbon 3 has an OH pointing up. That's this direction with relation to this hydrogen, okay? Carbon 4 is here. The OH is pointing down. So that's going to be equatorial there on that carbon. And at carbon 5, we have a CH2OH pointing up. That's going to be equatorial. And there's going to be a hydrogen pointing down on that back carbon, okay? So be familiar going backwards and forwards between these two drawings. and then being able to draw the Fisher projection or the Haworth projection from that, okay? All right. Let's do problem 2416. We've got beta-D galactopyranose. So step one, we want to grab the Fisher projection for galactose. Step two is to number your carbons and the oxygen that makes up the 6-membered ring. We know it's a 6-membered ring because we're talking about a pyranose. Step three, position your oxygen in that upper right-hand corner. Step four, draw your hatch marks. Step five, draw the hemiacetal hydroxyl group in the correct orientation given the beta, okay? Beta means up, alpha means down. So beta is up, so we draw that OH going up, okay? And that's carbon 1. The next step is to position all of the hydroxyl groups on your flat Haworth projection, okay? Right means down, left means up. So this OH, I'll do this in yellow, this OH is pointing to the right, so we want to point it down, that's here. This OH is pointing left, so we want to point it up. This OH is pointing left, so we point it up. This OH is pointing, well, that's the OH of the ring, actually, right here, right? So we don't do nothing with that. What we have is a CH2OH group pointing up, okay? For your D sugars, you're always going to have that CH2OH group pointing up. Now we need to do a chair conformation. So we do what I did before. You pull this carbon 1 down and pull carbon 4 up. So that's going to be a chair drawing that looks like this. Okay. And then using, I don't know, chapter 4 organic chemistry 1 technology, you fill in the groups. Remember that if something's up, it's going to be up in the ring. And you have two positions, right, with respect to like the plane. You have a upper substituent and a lower substituent, okay? So I'll just put in all my lines, bonds, in the correct bond angles, okay? And I'll just start filling things up. So this OH is up, that's definitely this way. This OH is down, that's this way. This OH is up, that's this way. This OH is up, that's way over here, okay? And my CH2OH is up, that's gonna be right here, okay? I won't do these other two problems because I think you understand the concept. It's very complicated, you need a lot of practice, and all of these structures are gonna be on Google. If you look up galactopyranose in the Haworth, in the Fisher, or in the chair, they're going to give you different structures for all three of those, okay? So that's how you do it, okay? You need to remember, is alpha or beta up or down? And if the OH is right or left in the Fisher projection, does that mean it's up or down in the Haworth projection? So you need to make a little note card for step by step how you go through that, okay? I'll leave it up to you to gain more practice. You're not going to learn more by watching me do a bunch of problems and look cool on YouTube, all right? All right. Now let's talk about furanose or furanose rings. What is the name of this molecule right here? This is called THF. We learned in General Chemistry 1 that it's a great polar aprotic solvent, and the F stands for furan. It's tetrahydrofuran. Okay. So a furanose ring is a 5-membered ring or a 5-membered ether, cyclic ether. Okay. This can come about by the cyclic cyclization of an appropriate sized ring, right? If the hydroxyl group at carbon 5 engages that carbonyl group at carbon 1 maybe it's easier if we show it kind of wrapping around first before we grab it in. Okay, so again, this is an addition reaction. We want to add this oxygen to the carbonyl carbon, and we want to take that hydrogen and add it to the oxygen, all right? And the double bond goes away to a single bond. And so that's going to give you, after a cyclization, a structure that looks like this. Okay, so carbon 1 is your aldehyde, okay? And again, we kind of draw this flat. This is still a Haworth projection, but and we position the oxygen at kind of like the middle top, okay, the 12 o'clock position, okay? So keep in mind that you can do this for the alpha isomer or the beta isomer, right? This one's pointing up, so is that alpha or beta? You need to remember that, okay? Now for fructose, here's what happens when D-fructose here on the left reacts to form a cyclic hemiacetal, okay? So it forms a furanose ring. Furanose, remember, means five-membered ring, and it's forming a hemiacetal. So again, remember that our anomeric carbon is here. It comes from carbon 2 of the carbonyl component, and that OH is pointing up, right? So that means it's the beta isomer. Now, this is not from an aldehyde, okay? This is a ketose. A ketose is a ketone, and remember that you can form cyclic hemiacetals and cyclic acetals from ketones or aldehydes. So this is a ketone here at carbon 2, okay? So I number this in a slightly different way, but what I have here, if we number it my way, is to start here with carbon 1. There's your carbonyl component. Carbon 2 is here, 3 is here, 4 is here, and then we want to do a five-membered ring. So the oxygen is carbon 5. So it's that sugar, it's the hydroxyl group that defines whether you have a D or L sugar. That's the hydroxyl group that's going to attack your aldehyde if you have these other ones like glucose, or attacks your ketone if you have things like fructose, okay? So that's your five-membered ring. If I number it my way, the purple characters here that I'm writing on the screen, okay? You can see how carbons 1, 2, 3, 4, and then that oxygen 5 give you that five-membered ring. Now, this hydroxyl group is attacking your ketone, and the oxygen of the carbonyl is pointing up, okay? So that's how you get the beta furanose, okay? So maybe let's do a couple of these, all right? Since I don't really have an example and then a problem, okay? So let's do this first one here. Okay, so first the problem says, draw the structures of the 2D aldotetroses. Each of these compounds exists as a furanose ring, which is formed when the OH at C4 attacks the aldehyde group. Draw each of the following furanose rings, okay? So what we have here is alpha D erythrofuranose, okay? So first thing I want to do is find out what the Fisher projection looks like for erythros. Okay, I found erythros in the textbook. Don't use erythrolose, which is a similar spelling and a completely different structure, okay? So make sure you get the one that's really close to the spelling, erythros, okay? So step 1 is to get this structure. Now, step 2 is to number your carbons, including that oxygen, to figure out what size ring is formed, okay? Furanose is a five-membered ring. A furanose is a five-membered ring. So we're gonna number this 1, 2, 3. If we go to the OH on the right, it's gonna be 4. That's not what we want. We want a five-membered ring, okay? So here's 4, and that oxygen is gonna be atom 5, okay? So that's gonna form your five-membered ring there, okay? Step 2 is to, number out things, all right? Step 3 is to use your template. So your template is the furanose, okay? And we always position that oxygen at the top, okay? Step 4 is to make your tick marks, okay? Carbon has 4 bonds, and the up and down, you know, those are the one way to indicate stereochemistry, okay? Now, step 5 is to take care of the alpha or the beta business, okay? So this is an aldehyde, so it means one of your groups is going to be an oxygen and the other group's going to be an OH when it changes to the hemiacetal. And so alpha means it goes down, okay? Alpha is down, so we want to put the OH pointing down. Now, since this is an aldehyde where the other group is a hydrogen, we can just do that, okay? So that's your carbon 1. We're at least we're almost done, okay? Now remember what we say, if we have the OH pointing to the right, it's pointing down in the structure, so this OH is pointing down, okay? And this hydrogen is pointing up. This OH is pointing to the right, so it's pointing down as well, okay? And this hydrogen is pointing up. Now carbon 4 is really easy if you think about it. What is attached to carbon 4? Okay, here's carbon 4 right here. This is connected to an oxygen, a carbon which is right here, and then 2 hydrogens. That's a CH2 group, so there's just H and H there. Okay, so that's how you do that problem. Okay, let's do problem D here. Beta D 3O-furanose. All right, so step 1, I want to find out what 3-ose is. So again, a number of my carbons. I set up my template. I make my tick marks. I address the beta issue. Beta means pointing up. So there's my OH pointing up, and there's the hydrogen pointing down. That's carbon 1, okay? If the OH is pointing to the left, it's pointing up as well. This OH is pointing to the right, so it's pointing down. And this is the same kind of molecule where we just have 2 hydrogens at carbon 4, okay? So that's beta D 3O-furanose, okay? Kind of complicated, but that's how you do that, all right?